Section 16.6, precipitation. So we're going to bring back this idea of the reaction quotient, that Q guy. We can better understand what's going on with a precipitation reaction by looking at this reaction quotient. So here we have an example that's wrong. Pause. So we're going to look at this generic equation, which I just fixed now. Calcium fluoride solid in equilibrium with calcium ion and fluoride ion. So this would be a dissolution reaction where this is dissolving, right? We can look at this reaction and write Q, the reaction quotient. That's going to be the calcium ion concentration times the fluoride ion concentration squared. Remember that 2 is because of this 2 over here. That looks a lot like the KSP. But KSP is the value of that product at equilibrium only. Q is the value of the product, and here the word product is the math term. The product of this times this. It's not this is a product and that is a product. This quantity here is Q under any conditions. So it doesn't have to have come to equilibrium. The way we calculate it is exactly the same. The difference is, are we using numbers that are at equilibrium or not? So remember that Q helps us to predict what direction a reaction will go in. So if we find that Q is less than KSP, that means that the solution is unsaturated and more solid can dissolve. If Q is equal to KSP, we have a saturated solution. If you add more solid, it will not dissolve. The solution's full. If Q is greater than KSP, the solution is supersaturated, and a solid will precipitate out of solution, usually. There are things like sodium acetate that take a little bit of nudging for that to happen.
We can go to the next slide yet.
Yeah.
Okay, I won't go to the next slide yet. Yes, question?
That all depends on, KSP depends on temperature, right? Like,
Yes, KSP is a single value at a particular temperature. We're assuming that we're not changing the temperature.
oh,
Yeah.
okay.
But KSP does change with temperature. Most things get more soluble when you heat them up. There are a few that get less soluble when you heat
But
them
we
up,
haven't learned
just
how
to be
put,
different.
like, temperature into the equation.
We have not learned how to mess around with that now.
Okay. This would just be like if we're doing like an experiment, you can, or like there's a problem and you're going to calculate Q and see is it at equilibrium or is it not at equilibrium?
Right. Yep.
So we can assume
We're going to
25
assume constant temperature.
25 degrees Celsius.
We're going to assume the temperature is whatever they gave us the KSP value for. Can I go to the next? Okay.
Thank you.
Because these are in OneDrive, you know. So we can use Q to predict if a precipitation reaction is going to happen when we mix two solutions. So the way we would do this is we will identify the potential precipitate, and then we'll calculate Q. If Q is greater than KSP, we can expect that there will be precipitation. So we'll do an example. A solution containing lead-2 nitrate is mixed with one containing sodium bromide to form a solution that, there's a word missing, that is 0.0600 molar in lead-2 nitrate and 0.0158 molar in sodium bromide, does a precipitate form in the newly mixed solution. And you're given the KSP for lead-2 bromide. Well, the first thing we have to do is identify the potential precipitate. And so in a question like this, you probably want to write out the balanced chemical equation. So I need a color that's visible first. We need the formulas for these reactants, which are actually given right here. Here's lead nitrate and sodium bromide. So we've got Pb, NO3, 2, mixing with, well, what's the state of that? It's aqueous. It's a solution, right? So that's aqueous. And it's mixing with sodium bromide, which is also aqueous. And then how do we predict the products? I didn't leave much space. Typical.
Are we predicting?
Yeah, how do we predict what products are going to form?
Associate, PBBR.
Yeah, look at that, I moved it. What kind of a reaction is this? This is Chem 1A stuff.
Ion?
Well, we're hoping it's a precipitation reaction, right? A double replacement reaction?
Yeah.
So what we're going to do is we're going to take the PB and the BR and put those together. We're switching partners, double replacement. And put the sodium with the nitrate. So we would end up with PB BR2 plus sodium nitrate. Come on. My iPad's being uncooperative. That's not working at all. Yes, feel free to laugh at me. I'm being absolutely ridiculous. There's not enough space. It's an iPad mini. It's tiny. And then we would need to balance that guy, right?
Yeah.
So we need a 2 here. And we'll get a 2 on this guy. Well, let's ignore this stuff in parentheses. I put that so we wouldn't have to flip over and look up a KSP. How would we decide which of these might be the precipitate?
Well, the nitrate.
Well, you know that nitrate compounds are always soluble. Sodium compounds are always soluble too. So that's not our precipitate. It's got to be the other one, right? So how are we going to predict if this will precipitate or not? Because we've learned now that even though something might be insoluble according to the solubility rules, if the concentrations are not high enough, it won't precipitate. So we're going to check Q, right? We need an equation here so that we can write the expression. So this is, kind of helpful here, but that's not what we need. So it would be for dissolving PbR2. When that dissolves, we get Pb2 plus aqueous plus 2Br minus aqueous. And the KSP for that reaction is given up here. So Q then equals the lead-2 ion concentration times the bromide ion concentration squared. Exactly the intonation I was going to use. Intonation stealer. What's the lead ion concentration?
Lead ion concentration.
0.0600. What's the bromide ion concentration? The other one. 0.0158 squared. Now, notice that in this equation, in this formula, there's a 1-to-1 ratio. There's one bromide ion in every one formula unit of sodium bromide. If this was like calcium bromide, CaBr2, then what would we have to do to this concentration to get the concentration of bromide ion? We'd have to double it, right? So be careful. Here, PbNO32, we've got twice as much nitrate, but we don't care about that. It's 0.06 molar in lead-2 nitrate, which is the same as 0.06 molar in lead-2 ion. Calculator now. So 0.06 times 0.015 squared. Yes. Thank you. I'm glad you're paying attention. That was a test to see if you're paying attention. Let's see, 1, 2, 3, 4, 5. So that equals, Q equals 1.50, I guess it would be, times 10 to the minus 5. 1, 2, 3, 4, 5. Anybody else get that? Yeah, so this is 3 sig figs, that's 3 sig figs, so I'm doing this as 3 sig figs. And then we compare that to KSP, that is Q.
Larger.
This is bigger, right? This is another one of those many situations where you've got bigger and smaller, unsaturated, supersaturated, connecting them. Easy to get confused. So I prefer to just think about it. So Q is telling me that these concentrations must be higher than they are at equilibrium. So is it going to precipitate?
Yes.
Yes. Yes, it will precipitate. Okay? You mix those two solutions, you will get a precipitate. Any questions? No questions. That's fine. Oh, yes? You want to see that some more?
Can you just repeat what you were saying about the untitled NABR?
Okay, so here, sodium bromide, we get 1 mole of bromide ion for every 1 mole of compound that dissolves. If we had a situation where we were, let's see, calcium would work. If we had calcium bromide, and that was equal to 0.0158, then the bromide ion concentration would actually be 2 times that. Okay? And so that's one of those little details it's very easy to miss on an exam, like when you're calculating the pH of calcium hydroxide. Any other questions? Nay. You want some hay with that? Selective precipitation. That's a process in which we're adding a reagent that will precipitate one of the cations that are dissolved in the solution, but not others. So it's selective. That reagent is chosen by examining KSP values. So if you find something with a very low KSP value, it's going to be very insoluble, right? And so that will precipitate out. Something with a higher KSP value may stay in solution. So in order for this to be effective, the difference in the KSP values needs to be a factor of at least 1,000. So one KSP value is 10 to the 3 times larger than the other. And to figure out what concentration is needed to precipitate or trigger, to precipitate the precipitation, trigger is better. The concentration needed to trigger the precipitation is determined by comparing Q and KSP. So a calculation very similar to what we just did. So let's do an example. So we've got a solution that has a magnesium ion concentration of 0.025 molar and a calcium ion concentration that's 0.011 molar. These ions can be separated by selective precipitation with potassium hydroxide. And the question is, what minimum hydroxide ion concentration will trigger the precipitation of the magnesium ion? And just to save us some time, I looked up the KSPs for magnesium hydroxide and for calcium hydroxide. So these differ by a factor of about 10 to the 5. So that's going to work. This is the smaller KSP, magnesium. So magnesium will precipitate first, and the calcium won't precipitate until you get to a higher concentration. So we're just looking at the magnesium then. So the chemical equation for magnesium dissolving is, it's helpful to write it out so that you don't forget to square the things that need to be squared. There's a 2 there. So Q equals the magnesium ion concentration times the hydroxide ion concentration squared. Fabulous. So we know what the KSP is. What's the situation where it will just begin to precipitate? Saturated. And at saturation, what's the relationship between Q and KSP?
Equal.
They're equal. So we want Q to be equal to KSP. KSP is 2.06 times 10 to the minus 13. And so that's going to be equal to the magnesium ion concentration, which was given up here, 0.025, times the hydroxide ion concentration squared. So the hydroxide concentration that we need, the minimum, is going to be equal to the square root of 2.06 times 10 to the minus 13 divided by 0.025. Two point 2.9 times 10 to the minus 7. 6, 10 to the minus 6. Anybody else get that number?
Yes.
Thank you.
Sometimes we have to do a cube root. I know on like the final, we can't use our fancy calculators. Are we gonna have to remember how to do a cube root?
Put it to the 1/3 power.
Really?
Yeah.
Yeah.
Yeah, raise it to the 1/3 power. It's a good question, though. Turns out this TI-36X Pro it's not technically a programmable calculator. It's not a graphing calculator. It can be used on like the SAT and stuff.
I bought it.
They have some other ones that are usable on those and makes they do integral.
Yeah, well, this one does all kinds of stuff. It's awesome. And it's less than $20.
Really?
Yeah. So any questions about this one? No? Okay. Yes.
I have a question about that one.
You're
the
slow.
last one.
There you go.
I am slow.
Yeah, it's okay. Delayed response.
So when we add the OH,
Mm-hmm.
like some amount of that will precipitate. Will no calcium precipitate at all?
We could figure out the concentration needed to precipitate calcium.
So, but you're saying like if I add some, it's gonna do the magnesium all before
It's
this?
going to do the magnesium first,
All of
because
it?
we can actually do this without really doing a whole bunch of math here. We just need to plug in this KSP. So it's the square root of 5.68 times 10 to the minus 6 divided by 0.025. What? Domain error. I don't know. I did something wrong.
Break it?
Did you use the?
Yeah, I broke the
You
calculator.
still use the 0.25 and you wouldn't use the 0.11?
I would use the 011, thank you. Brain overload.
Okay, I got it. 0.0227.
0.0227.
Yes.
So you'd have to get up to a hydroxide ion concentration of 0.0227 before any of the calcium would begin to precipitate. So up until that point, only magnesium would precipitate.
I guess what my question is, if we have one that's like the KSP is 10 to the negative 13,
Mhm.
we have another one that's like 10 to the negative 11. Will both of them precipitate? Like,
You won't get a good separation because the difference there is only a factor of 100.
So if
And
that
so
guy's
there'll
1,000
still be, there'll be more of the first ion precipitating left by the time the second one starts precipitating, and it won't separate as well. Are you going to ever get a perfect separation?
Yes.
No.
Not-
No, never. Because even things that we say are completely insoluble.
Okay.
Well, what if you have 50 liters of water and one formula unit dissolves? Is that I mean, that's dissolving, right? And so, we kind of have to be okay with things not being absolute. It's disturbing. I don't like it either. So any more questions about this problem? I need to wait longer for you, right? Yeah. Okay. We can also figure out the concentrations of ions that are left in solution after selective precipitation. Doesn't that problem look like it has way too many words in it?
Yeah.
Yeah. It's okay. So a solution is 0.085 molar in lead 2 ion, 0.025 molar in silver ion. There's two questions here. A, if selective precipitation is to be achieved using sodium chloride, what minimum concentration of sodium chloride do you need to begin to precipitate the ion that precipitates first? And again, I wrote the KSPs for both of them down here so we could look at that. Which ion's going to precipitate first? The one with the smallest KSP. Okay, so it's going to be the silver. So silver is going to precipitate first. And how do we figure out the concentration of sodium chloride needed to precipitate that? We find the point at which Q equals KSP,
Yeah.
right? So I'm going to try to be a little more conservative of space here. So we've got silver chloride, and that when that dissolves, we get silver and chloride. Fancy. So we want Q to be equal to KSP. KSP is 1.77 times 10 to the minus 10. And that equals the silver ion concentration, which we're given, 0.025, times the chloride ion concentration. So that's a simpler calculation. 1.77 times 10 to the minus 10 divided by 0.025. I'm going to tell my calculator to show me this in scientific notation because that's just, I don't want to count that many zeros. So the chloride ion concentration, when it starts to precipitate, will be 7.0 times 10 to the minus 9th molar. It's pretty small. So that's the minimum concentration of sodium chloride to begin precipitating that ion. So that's similar to the problem we just finished. Now the second part, what is the concentration of each ion left in the solution at the point where the second ion begins to precipitate? Well, we need to find the point at which the second ion begins to precipitate. So we're going to do this same calculation for lead to find out what that concentration is. So when lead dissolves, lead chloride, we get a lead ion and 2 chloride ions. Stoichiometry is important here. PbCl2. So, yeah. So again, Q needs to equal KSP. I like you guys. You're so fun. KSP is 1.17 times 10 to the minus 5. So that equals the lead concentration, 0.085, times the chloride ion concentration squared. Okay, so I'm not going to write all that out. I'm going to it's the square root of 1.17 times, that's the wrong button, times 10 to the minus 5, divided by 0.085. I know, it's a little disturbing, isn't it? The chloride ion concentration comes out to 1.17 times 10 to the minus 2. I think it's just a fluke that it's 1.17. It's nothing. It's like when you go to the grocery store and you check out and it comes out exactly $100. You're like, oh, that's crazy. Does it mean anything? No, it doesn't. Yes. Pardon me? I did take the square root of it. So this is the chloride ion concentration at which the lead begins to precipitate. How are we going to figure out how much silver ion is left?
The difference.
Yeah.
Q and KSP.
Silver ion.
Well, basically we have
Done by now.
an equilibrium thing going on, right?
Oh, ice table?
Yeah, I think we need an ice table. I did this on Monday, so I don't remember. This is making things up as I go along. It's been pretty effective. So we need to look at the silver. And here's the chloride. So the initial concentration of the silver was 0.025, right? And now we've added enough chloride that the chloride concentration would be this, 1.17 times 10 to the minus 2. I mean, we could do a real ice table and subtract things and do stuff like that, but do we really need to? No, we don't. We can just say, well, this silver is going to decrease by X, and this is going to decrease by X, right?
Yeah.
Because it's going to precipitate. Not 2X. This is silver chloride.
Oh, okay.
That's the other one.
Same thing.
Yeah. So then we would get 0.025 minus X times 1.17, bless you, times 10 to the minus 2 minus X. And that would equal KSP, right?
Question.
Yes, question?
Why did you use the 1.17 times 10 to the negative 2 for chloride ion as opposed to the 7.0 times 10 to the negative 9?
Well, because what's happening here, when we added this much, the silver started to precipitate.
Yeah.
Now they're saying, look at the point where the other ion starts to precipitate. And that's going to be a concentration of this.
Yeah. That's the total amount that has been added.
Yeah, so if we consider this to be the total amount added, what do we end up with here? So I'm just going to do that on my solver, because I think that's a lot easier. 1.77 into the minus 10. And then I've got 0.025 minus X times 1.17 times 10 to the minus 2 minus X. I don't remember if this is exactly the way I did it before.
Little things on the solver.
So I'm getting X equals 0.025 00013 something.
Oh, wow.
Impossible.
So that's not possible, is it?
I got a different.
So this then is not the right direction to go with this.
I got doing the same thing. I got a different number too.
What'd you get?
0.0117,
That's what I got.
Okay.
which is just to add another.
Such boundaries.
So that's
I will
a problem
just,
too.
I'll, you know.
Both of them are problems.
Yep, so now, so that's one, and that one doesn't work because it's a little bigger.
That one.
Why doesn't .0117 work?
Because that's your other number.
Oh, because it's the other number. Yeah, it is too close. Well, I'm getting .011699986, which is slightly smaller than .0177. I mean .0117. But this is not going to come out to a, we're not going to be able to find a number, right? So let's say, okay, maybe we need to do it the other way around. So I'm going to erase this.
Doesn't work, erase.
Yeah, if it doesn't work, erase, start over again. I could just go to another page, but then I have to write a bunch of junk over. Well, silver chloride is not very soluble, correct? So let's assume that it's all going to precipitate, and then let's calculate the little bit that's left instead and see if that comes out better. So which number is smaller? 1.17 times 10 to the minus 2 or 0.025? So let's write this in decimal form.
Oh.
Which one's smaller?
There you go.
0.0117 is smaller, right? So this will be 0.025 minus 0.0117. And this is going to be essentially 0. Okay? So what's that come out to be? 0.025, oh, quit. 0.025 minus 0.0117. 0.0133. So if it all reacted, this is how much silver we would have left. If all of this chloride reacted with the silver, that's how much we would have left.
That's where you stop adding chloride.
Right. We added chloride to that point, and now the lead will just begin to precipitate, but at this point, this much of the silver remains. Well, let's do a calculation with this. Sorry, this is just, it's not very pretty. So if we take this as the initial concentration and 0 as the initial concentration, and then we need an X in here somewhere, right? So the chloride is going to be our X, and this number plus X is going to be our silver ion, because a little bit is going to dissolve back according to KSP. Does that make any sense at all? No? Oh, sheesh. Let's do this. I need space. I think we're done looking at all those words. Goodbye, words. In the way. Let's do this again. Silver and chloride. So I'm saying that it all reacted, and this is essentially 0. But we're going to call that our initial value now. We say it all reacted, but now it's going to come back a little bit. And so this is going to be plus X, and this is going to be plus X. So we'll end up with 0.0133 plus X and X. That's what happens when you erase white. You see the letters underneath. So 1.77 times 10 to the minus 10 is going to equal x times 0.0133 plus x. So x comes out to be 1.16999 times 10 to the minus 2. It doesn't, no, I'm not sure about that. This is not looking at all right. Again, I'm making sure that you're paying attention, right?
Very close number. I think the other one.
So that's one root, and that root doesn't make any sense. The other root is 1, 2, 3, 4, 5, 6, 7, 8. Like that one better?
Yeah,
Okay,
that's
yeah.
more like it.
This one doesn't make sense, does it? It doesn't make any sense at all.
Where's that?
That's essentially the same chloride ion again.
Right. So this is telling us that the chloride ion concentration is that little tiny number. When we add that to 0.0133, does it make any difference? No. So we didn't really have to do all that fun stuff, did we?
Actually small. But we don't know that.
I just, wanted to torture you. As usual, yes. I'm really big into torturing people. So the silver ion concentration is 0.0133 molar. And technically, we can only have 2 sig figs on that. What's the other, we need to know the other ion as well, right?
Yeah.
It's like magic. It's just, isn't that fun? So much better than getting chalk all over your hands or dealing with dry erase markers that run out all the time. It's like one of those dumb little things we had to keep us quiet in church. You scribble over it with a pencil and a picture appears. You guys are way too young for that, sorry.
Yeah.
Okay. How do we figure out the concentration of the lead ion?
Same way.
What's it going to be close to, do you think?
It's
It's going to be close to this, isn't it?
Yeah.
Because didn't we just calculate the amount that was needed to precipitate it? I think it's pretty safe to say that the lead-2 ion concentration is going to be the same as it started out. Because this is a point where we've added just to where it's saturated. Any questions?
But some of that fluorine was taken away from by that silver. So now it's even lower concentration, shouldn't it be? So then do we need
Yeah, see, that's a thing in the problem that's not made real super clear. If I add 1.17 times 10 to the minus 2 molar chloride, or make the solution be that, is it really that? Well, the chloride took some of it,
Yeah.
right?
The silver took the silver. Yeah.
and it's even less? So then there's not enough.
So we're checking the answer in the book, and it says that I did this wrong. It says that it's 1.5 times 10 to the minus 8. So I realized my mistake. Can you guys figure it out?
Oh.
Look at smarty pants, right? There's a flaw in how I set all this up. There's a flaw. So this chloride ion concentration, 1.17 times 10 to the minus 2, that is after the chloride, some of the chloride that we've added has been precipitated out by the silver,
Yes.
right? So it's not there anymore. So I'm just going to, we've got all these numbers memorized, right? That's fun too. So we don't need that. No, we did need that. We don't need this part. We need KSP. That's the wrong answer. I'll get rid of that. There it is. Okay. Let's try this again. So we've got silver, we've got chloride. The chloride ion concentration at equilibrium is the 1.1. Oh, let's not do the scientific notation. The 0.0117. We're going to add chloride until the concentration is 0.0117. At that point, the lead will precipitate. But this has already precipitated some of the silver. The silver started out at 0.025 molar. That was our initial. Chloride was essentially 0. And that's an E because I forgot the bar in the middle. And so then the change is that this went up 0.0117 and this went down 0.0117. No. Okay. Okay, so you know how you guys sometimes struggle on these worksheets and you go around and around in circles?
Yes.
Sorry, that doesn't go away once you get a degree. You still make mistakes. I'm making this way too hard. Just like you did, some of you did on the exam. That's the equilibrium concentration. We want to know what this is. That's it. Oh, yeah, okay. 1.77 times 10 to the minus 10 equals x times 0.0117. .77 times 10 to the minus 10 divided by 0.0117.
Yep.
There we go.
Yeah.
Now, it depends on how the question was asked. If the question asked if you added 0.0117 molar enough to make it, then our previous answer would be correct, but alas.
So our x is going to be.
Okay, now I'm sure I lost some people in that mess. You want me to just start over? Yeah, let's start over.
Is all this going to